Assalamualaikum and hi. Before I start my introduction, first of all, I want to introduce my team members. We are from Group 8. We are 3 members. First, Alexander. Second, Jamie. Third, me, Aiman. So we present about the proposal page 3, which is the fire suppression system design. For the introduction, this project apply fluid mechanics principle, which is such as the Bernoulli equation and heat loss calculation. To design a fire suppression system for a 3-story building, our goal is to determine the optimal pipe diameter and pump performance required to deliver sufficient water pressure to the highest floor. For problem framing, point 1, which is the catastrophic fire risk. In high-rise and multi-story building, fire presents a catastrophic risk to all occupants. Once an ignition occurs, deadly flames and toxic smoke spread rapidly upward to vertical shaft and stairwell, quickly blocking critical evacuation routes and creating immense panic. A delay of just a few seconds can trap people inside the upper floor, drastically shrinking their chances of survival. In this critical moment, as temperature spikes and smoke density rises, active fire protection becomes our absolute primary line of defense. Therefore, ensuring an immediate, automatic, and highly reliable water delivery system is not just a matter of regulatory compliance or hitting numbers on paper. It is strictly a matter of life and death, serving to control the thermal energy before it causes full structural failure and mass casualties. Point 2, which is the hardest to supply area. From a fluid mechanic perspective, the highest floor of the building is always the hardest to supply area because it is located furthest from the water source. To deliver water effectively to this zone, the floor must overcome massive gravitational resistance known as elevation heat. At the same time, the fluid faces high frictional heat loss as it travels through long vertical riser, bends, and isolation valve. This accumulated resistance results in a severe drop in pressure before the water can even reach the sprinkler nozzle. For the point 3, which is the consequences of incorrect pump selection. If we select the wrong pump that failed to match our required flow rate and heat, the consequences are devastating. Under insufficient pressure, the system will experience a severe operating drop. Instead of discharging a high-velocity fire suppression spray, the nozzle will only produce a weak water trickle. This technical failure completely destroyed the system's ability to control the fire at an early stage. Consequently, this leaves critical zone unprotected, leading to catastrophic structural damage and an extreme risk to human life. Therefore, to eliminate these engineering risks, precise hydraulic calculations are an absolute necessity. I think that's all of my part. Thank you.
My name is Alexander Yuzen King. 108794 is my matrix number. Now I will continue with diagnostic finding parts. First, hydraulic analysis. Let us look at our system requirement. Our analysis showed that if we want to supply water to the top floor, we must overcome a total head loss of 3.748 meter, which account for both major friction losses of 0.678 meters and cumulative minor losses of 3.07 meters across our 12 pipeline fittings. Next, let's move on to the structural integrity and elbow forces. While hydraulic efficiency is vital, we also prioritize structural safety by performing a momentum analysis on the